Welcome back. Today we are exploring how resistors can be grouped together in electrical circuits and how they affect the flow of current. So let's dive into series and parallel combination of resistors. In any electrical circuit, you'll find a variety of components: batteries, resistors, capacitors, inductors, and more. And these components control the flow of current. Now, resistors come in two types of combinations: series combination and parallel combinations. Now, if we group these resistors as a single resistor, it is important to understand how to define total or equivalent resistance. We define the equivalent resistance of the combination as a single resistance which allows same current to flow as the given combination when the same potential difference is applied across it. Series combination of resistor is formed by joining the resistors end to end such that the same current passes through all the resistor. Consider two resistors R1 and R2 connected in series. The combination is connected to a battery at the ends A and B. Suppose the current I flows through the series combination when it is connected to a battery of voltage V. The potential difference V1 and V2 is observed across the resistors R1 and R2 respectively. So V1 across the resistor R1 can be written as I times R1. Similarly, V2 is equal to I times R2. Sum of V1 and V2 gives the total potential V. Therefore, substituting I times R1 plus I times R2. Taking I common, R1 plus R2. If R is the equivalent resistance across the combination, then V can be written as I times R. Therefore, R is equal to R1 plus R2. Thus, the total or equivalent resistance of series combination is R is equal to R1 plus R2 plus R3 plus R4 so on till the number of resistors in series. This is great when you want to limit the current in a circuit. For example, in a string of Christmas lights or two lamps connected in series, the voltage across each lamp will be less than the total voltage supplied by the source. If one lamp goes out, the entire circuit is interrupted because the current has nowhere to go. Parallel combination. Parallel combination of resistors is formed by joining their one end at one point and other end at another point. In parallel combination, same potential difference exists across all resistors. Consider two resistors R1, R2 connected in parallel. The combination is connected to a battery of voltage V which draws a current I. The main current I divides in two parts. Let I1 be the current flowing through the resistor R1 and I2 be the current flowing through the resistor R2. Then I1 is equal to V by R1. I2 is equal to V by R2. The main current is the sum of I1 and I2. So I is equal to I1 plus I2. Substituting this, V by R1 plus V by R2. Taking V common, 1 by R1 plus 1 by R2. If the equivalent resistance of combination is R, then we can write V is equal to IR. So I is equal to V by R. Therefore, we get 1 by R is equal to 1 by R1 plus 1 by R2. R is equal to R1 R2 by R1 plus R2. Thus, in parallel combination, the reciprocal of equivalent resistance is equal to the sum of reciprocals of individual resistors. So, the total resistance in parallel combination is always smaller than the smallest individual resistance. That means the more resistors you add in parallel, the lower the total resistance and greater the total current drawn from the source. This is why most electrical appliances in our homes like lamps, fans and heats are connected in parallel. This way, each appliance gets the full 220 volt supply and the current flowing through each appliance is independent of others. As more devices are added, the overall resistance of the circuit decreases and more current is drawn from the main supply. Let us now look at some example. Consider this example. For the circuit shown in the figure, calculate the value of resistance R2 and the current I2 flowing through it. this is the problem with parallel combination of two resistors. So the equivalent resistor R is equal to R1 R2 by R1 plus R2. We know that R1 is 10 ohms. So 10 R2 by 10 plus R2. From Ohm's law, we can calculate the equivalent resistance R equal to V by I. V is 50 volt, I is 10 ampere, so the R is 5 ohm. Substituting this here, 5 is equal to 10 R2 by 10 plus R2. 50 plus 5 R2 is equal to 10 R2. So 5 R2 is 50, which means R2 is equal to 10 ohm. So we get this to be 10 ohm. Since the resistance are equal, that is R1 and R2 both are 10 ohm, the current will be equally divided between them. Therefore, I2 is equal to I by 2. We know that I is 10 ampere, so 10 by 2 is equal to 5 ampere. Let's move on to another example. For the circuit shown, calculate the equivalence resistance between the points A and D. This is a parallel with equivalent resistance Rp, and then this 5 ohm Rp and 7 ohm in series. R1 R2 by R1 plus R2, which is 15 into 3 by 15 plus 3. 15 threes are 45. 15 3 plus 18. This is 2, this is 5. So 2.5 ohm. Between the points B and C, the equivalent resistance we found is 2.5 ohm. Now this 5 ohm, 2.5 ohm and 7 ohm are in series. So in R between resistance of AB, resistance BC, resistance CD. Since it is a series combination. So 5 plus 2.5 plus 7. Summing up, we get this as 14.5 ohm is the equivalent resistance between the points A and D. Let us look at another example. Refer to the network shown in the figure. Calculate the equivalent resistance between the points B and C, C and D, and A and E. This looks like a complicated, but let us break it down. First is across the resistor, so across the points B and C. Three resistors are in parallel combination. The next is between the points C and D. It's two resistors in series combination. Next is between A and E. This will, after calculating the equivalent resistance between these two, we'll simplify it. First, let's move on to calculate the equivalent resistance between the points B and C. We know that for a parallel combination, the reciprocal of equivalent resistance is the sum of reciprocal of individual resistance. So 1 by RBC is 1 by 5 plus 1 by 10 plus 1 by 30. Simplifying this is 6 plus 3 plus 1. Equivalent resistance between the points B and C is 3 ohm. Let's move on to the points between C and D. Two resistors series combination. So the equivalent resistance RCD is 2 ohm plus 4 ohm. So we get 6 ohm. Let's redraw this again. Then there is a 3 ohm resistor. Then there is point B. Between point B and C, we found that the resistance is 3 ohm. 3 ohm. Now this is point C. Between point C and D we found it to be 6 ohm. So this is 6 ohm. This is point B. If you observe, there is no resistance between the points D and E. So the point D and point E are the same. And then this is the parallel combination between B and E. So here there is a 7 ohm resistor and 3 ohm resistor. This is the point E. First, let us calculate this parallel combination. This one. This point is B. This point is E. 1 by RBE is 1 by 7 plus 1 by 3. 21. So we found RB is equal to 21 by 10 ohm. Let us draw that here. What did we find? We simplified this to be this resistor. This is 21 by 10 ohm. So RBD can be 3 plus 6, 9 ohm. This is the point A. There is 3 ohm. This is the point B. The resistor is 9 ohm. Point B. And there is this one is 21 by 10 ohm. We want to calculate between A and E. If you observe, this is a parallel combination. 1 by RBE is equal to 1 by 9 plus 1 by 21 by 10. So we take 63, 9 sevens are 63, 21 threes are 63, so 30. So RBE is equal to 63 by 37, which we get around 1.70 ohm. RAE is 3 ohm plus 1.70 ohm, which is equal to 4.0 ohm. This is the final answer.
These steps involve breaking down the complex circuit into manageable parts and calculating the resistance for each combination, whether in series or parallel. As you practice, you'll get better at solving these problems step by step. To summarize, in series combination, add the resistances to get the total resistance, and in parallel combination, the reciprocal of total resistance is the sum of reciprocal of individual resistance. Thanks for watching. I hope this helps you understand how resistors work in different configurations. Don't forget to like, share and subscribe. If you have any questions, drop them in the comments below.